You're sitting in 23C on a Tuesday afternoon flight from Newark to Denver. 3 hours and 45 minutes in a metal tube with 180 other people. The guy in 23B coughs. Not a polite cough. A deep, wet, rattling cough that sounds like his lungs are trying to escape. He does it again and again. For the next 2 hours, he's coughing every 30 seconds. You're breathing the same air as this guy. You're trapped. The flight attendants can't do anything. You can't open a window. You're just sitting there inhaling whatever virus or bacteria this person is exhaling, and you absolutely know, that in 3 days you're going to be sick. Here's the question nobody asks. Why? Not, why is that guy sick on a plane? That's obvious. But why does being on a plane make it so likely that you'll catch whatever he has? Is it really just because you're in an enclosed space? Or is there something about the air itself? Turns out there's an entire hidden system governing the air you breathe at 35,000 feet. A system of engineering compromises, economic calculations, and regulatory battles that most passengers have no idea exists. The air in an airplane cabin isn't like the air in your house or your office or even a hospital. It's carefully controlled, heavily filtered, and constantly recycled. But it's also complicated. And after COVID-19, after we all became amateur epidemiologists obsessed with airflow and ventilation, the question got a lot more urgent. Is the air on planes actually safe? Are airlines doing everything they could to protect passengers? Or are their corners being cut? Tonight, we're going deep into the engineering, the economics, and the politics of cabin air. We're going to understand exactly what you're breathing when you fly, why it works the way it does, and what airlines fought for decades to avoid telling you. This is Hours Deep. Get comfortable. We're taking off. Let's start with what most people assume. The air in a plane is recirculated. You're breathing the same air over and over, mixed with whatever germs and viruses everyone else is exhaling. That's partially true. But it's more complicated than that. Here's how it actually works. Modern commercial aircraft, we're talking Boeing 737s, Airbus A320s, the planes most of us fly on, use what's called an environmental control system, or ECS. The ECS does two things. It provides breathable air, and it regulates temperature and pressure in the cabin. The air comes from outside. Specifically, it comes from the engines. Wait, the engines? The things burning jet fuel at 500 degrees? Yes, but not from the combustion chamber, from the compressor. Jet engines work by compressing air, mixing it with fuel, and igniting it to create thrust. But in the early stages of the engine, the compressor section, the air is just compressed, not burned. It's hot and high pressure, but it's clean. This compressed air, called bleed air, is tapped off from the engine and routed to the cabin. On the way, it goes through a series of cooling systems, heat exchangers, turbines, condensers that bring the temperature down from around 400 degrees Fahrenheit to something breathable, around 70 degrees Fahrenheit. That's your fresh air. It enters the cabin through vents in the ceiling, flows down through the cabin, and exits through grills near the floor. From there, it's either vented overboard or sent back into the system. Here's the key part. Modern aircraft recirculate about 50% of cabin air. Half the air you're breathing is fresh from outside, via the engines. The other half is recirculated, air that's already been in the cabin, breathed by passengers, and then filtered before being mixed back in. Why recirculate at all? Why not just use 100% fresh air? Two reasons: fuel efficiency and humidity. Bringing in outside air requires running the engines harder, which burns more fuel. Recirculating air is free. It's already pressurized and temperature controlled, and if you used 100% fresh bleed air, the cabin would be extremely dry. At cruising altitude, outside air has almost zero humidity. Recirculating some cabin air, which picks up moisture from passengers' breath and sweat, keeps the humidity from dropping to desert levels. So, 50% fresh, 50% recirculated. That's the standard. But here's the critical question. What happens to that recirculated air before it gets mixed back in? It goes through a filter, specifically a HEPA filter. HEPA stands for High Efficiency Particulate Air. These filters are the same technology used in hospital operating rooms and infectious disease wards. A HEPA filter works by forcing air through a dense mat of randomly arranged fibers, usually made of fiberglass. The fibers create a maze that traps particles, and they're incredibly effective. A true HEPA filter captures 99.97% of particles that are 0.3 microns in diameter. How small is 0.3 microns? For reference, a human hair is about 70 microns. Bacteria are typically 1 to 10 microns. Viruses, like influenza or COVID-19, are much smaller, around 0.1 microns. But here's the thing. HEPA filters are actually better at capturing very small particles than medium-sized ones. It's counterintuitive, but it has to do with physics. Tiny particles bounce around randomly, Brownian motion, and stick to fibers more easily. So a HEPA filter captures bacteria, viruses, dust, pollen, mold spores, basically anything airborne that you'd want removed. Most modern aircraft, Boeing 737s, 777s, 787s, Airbus A320, A350, are equipped with HEPA filters. The recirculated air passes through these filters before being mixed with fresh bleed air and pumped back into the cabin. In theory, this means the air in a plane is cleaner than the air in most buildings. The air in your office? No HEPA filter. The air in a restaurant? Definitely not. Even hospitals don't filter all their air through HEPA. Only specific rooms like I see us in operating theaters. Airlines love to point this out. The air on our planes is refreshed every 2 to 3 minutes. HEPA filters remove 99.97% of particles. Cabin air is cleaner than your home. And technically, they're not wrong. But there's always a but. Problem number 1. Not all planes have HEPA filters. Older aircraft, some 737s, MD-80s, regional jets, were built before HEPA became standard. Some airlines have retrofitted them, others haven't. There's no federal requirement in the U.S. that commercial aircraft use HEPA filters. The FAA regulates airworthiness and safety, but cabin air filtration, that's up to the airline. Some airlines advertise their HEPA-equipped fleets. Others don't mention it at all. As a passenger, unless you specifically research the aircraft type and the airline's fleet specs, you have no idea if your flight has HEPA filtration. Problem number 2. HEPA filters only work on recirculated air. Remember, 50% of cabin air is fresh bleed air from outside. That air doesn't pass through a HEPA filter. It's already clean. There's no bacteria or viruses at 35,000 feet. But it also means the 99.97% filtration claim only applies to half the air. Problem number 3. Airflow matters as much as filtration. Even with HEPA filters, if the air isn't circulating properly, you can still have pockets of contaminated air. Cabin air is designed to flow vertically, down from the ceiling out through the floor. This minimizes lateral spread. In theory, the air around you comes from above, flows down past you, and exits below, without mixing much with the raws in front or behind. But in practice, people move, air turbulence disrupts flow, passengers adjust overhead vents. The system isn't perfect, and here's the big one. The air doesn't change instantly. It takes 2 to 3 minutes for a full cabin air exchange. If someone 2 rows up sneezes, their respiratory droplets can linger in the air for a minute or more before being filtered out. That's enough time to reach you. Problem number 4. Airlines can adjust the airflow rate. This is the part airlines don't advertise. The environmental control system has settings. Pilots can adjust how much fresh air is brought in and how fast the recirculation happens. More airflow equals cleaner air, but also more fuel consumption. Less airflow equals saves fuel, but air quality declines. The FAA sets minimum ventilation requirements, 10 cubic feet per minute of fresh air per person. But that's a floor, not a ceiling. Airlines can exceed it if they want, or they can run right at the minimum. Guess which option is cheaper? During the 2000s, when fuel prices spiked, some airlines reportedly reduced cabin airflow to save money. Passengers complained of stuffiness, headaches, fatigue. But there was no regulation against it as long as they met the FAA minimum. After COVID, airlines rushed to assure the public that they were running airflow at maximum rates. But there's no way for passengers to verify this. No display in the cabin showing real-time air exchange rates. You just have to trust them. Let's go back. Way back. In the early days of commercial aviation, 1920s, 1930s, cabin air wasn't a concern because cabins were barely enclosed. Planes flew low, under 10,000 feet, where the air is breathable without pressurization. Passengers wore heavy coats because it was cold. Windows rattled. The air inside the cabin was basically the same as outside, fresh, but freezing and noisy. Then came World War II and the development of high-altitude bombers. Engineers figured out how to pressurize aircraft cabins, allowing planes to fly higher, faster, and more efficiently. After the war, this technology moved to commercial aviation. The Boeing 307 Stratoliner, introduced in 1938, was the first pressurized airliner. By the 1950s, with jets like the Boeing 707 and Douglas DC-8, pressurized cabins became standard. Now planes could cruise at 35,000 to 40,000 feet. Where the air is too thin to breathe, the cabin would be pressurized to simulate an altitude of 6,000 to 8,000 feet, equivalent to Denver or Mexico City. Uncomfortable for some, but survivable. But pressurization created a new problem. Where does the air come from? You can't just bring in outside air at cruising altitude. It's minus 60 degrees Fahrenheit and has almost no oxygen. You need a system to compress it, heat it, and regulate it. Hence, bleed air from the engines. For decades, this system worked fine. Nobody questioned it. Air quality wasn't a major concern. Smoking was allowed on planes until the 1990s. So, if you were worried about breathing clean air, you were in the wrong place anyway. The first cracks. Sick building syndrome. In the 1980s, something strange started happening. Not on planes, but in office buildings. Workers in newly constructed, energy-efficient buildings began reporting mysterious symptoms: headaches, fatigue, dizziness, respiratory problems. difficulty concentrating. Doctors couldn't find a specific cause. The buildings were clean, modern, well-maintained. Researchers eventually traced the problem to ventilation. In the 1970s energy crisis, buildings were designed to be airtight to save on heating and cooling costs. But this meant less fresh air circulation. Indoor air was recirculated more, and pollutants from carpets, paints, cleaning products, even office equipment built up to unhealthy levels. This became known as sick building syndrome. The solution? Better ventilation. ASHRAE, the American Society of Heating, Refrigerating, and Air Conditioning Engineers, updated standards to require more fresh air in buildings. But airplanes still operating on the old model. In fact, as fuel prices rose in the 1980s and 1990s, airlines were moving in the opposite direction, reducing fresh air to save fuel. Aerotoxic syndrome. In the late 1990s and early 2000s, pilots and flight attendants started reporting strange symptoms: memory problems, tremors, respiratory issues, chronic fatigue. Some researchers called it aerotoxic syndrome. The suspected cause? Contaminated bleed air. Remember, bleed air comes from the engine compressor. Normally, it's clean. But if there's an oil leak or a mechanical failure, engine oil or hydraulic fluid can get into the bleed air system. These fluids contain organophosphates, toxic chemicals also found in pesticides. Inhaling them can cause neurological damage. Fume events. Incidents where passengers or crew smell oil or chemicals in the cabin were being reported more frequently. Some were minor, others were severe, forcing emergency landings. The aviation industry pushed back hard. Boeing and Airbus insisted that bleed air was safe, that fume events were rare, and that there was no scientific consensus linking cabin air to long-term health problems. Regulatory agencies like the FAA and EASA, European Aviation Safety Agency, conducted studies. The results were inconclusive. Some studies found elevated levels of toxins in cabin air during fume events. Others found no long-term health effects. The industry argued that aerotoxic syndrome wasn't a real diagnosis, just a catch-all for unrelated symptoms. Flight attendant unions disagreed. They pushed for mandatory air quality monitoring, better filters, and alternative systems that didn't rely on bleed air. Which brings us to a critical question. If bleed air is potentially dangerous, why do we still use it? The engineering answer. Bleed air systems are simple, reliable, and lightweight. You're already running jet engines. Tapping off some compressed air for the cabin is easy. Just a few valves and ducts. No extra compressors, no heavy machinery. The alternative? An electrically driven air conditioning system, where compressors are powered by the plane's electrical system instead of bleed air. Boeing's 787 Dreamliner, introduced in 2011, uses this system. No bleed air. Electric compressors provide cabin air. This eliminates the risk of engine oil contamination, but it's also heavier and more complex. More components that can fail. More electrical load. For Boeing, it made sense on the 787 because the plane was already designed with a more electric architecture, more systems powered by electricity instead of pneumatics or hydraulics. But retrofitting older planes? Not practical. Too expensive. So most aircraft still use bleed air. And the debate over aerotoxic syndrome continues. Enter COVID-19. Then came 2020. Suddenly, everyone cared about cabin air. Could you catch COVID-19 on a plane? How risky was flying? Should airlines be doing more to filter the air? Airlines scrambled to reassure passengers. They ran ads highlighting HEPA filters. They published studies showing that cabin air exchange rates were higher than most indoor spaces. They pointed to research suggesting that airflow patterns minimize transmission risk. And to be fair, some of that research was legitimate. A 2020 study by the Department of Defense, in partnership with United Airlines, used mannequins and aerosol tracers to simulate respiratory droplet spread in a cabin. The results were surprisingly good. With masks and normal ventilation, the risk of transmission was low. Particles were quickly filtered out. Another study found that the vertical airflow in cabins, air moving down, not side to side, meant that even if someone a few rows away was infected, their exhaled air was less likely to reach you, compared to, say, sitting next to them in a restaurant. But there was a catch. All of these studies assumed the ventilation system was running at full capacity. If airlines were dialing down airflow to save fuel, which, remember, they're allowed to do, the risk would be higher. And there was no way for passengers to verify. The economics, why airlines resist change the cost of clean air. Let's talk money. Running the environmental control system at maximum airflow burns more fuel. How much more? It's hard to find exact figures. Airlines don't publish this data. But industry estimates suggest that reducing cabin ventilation by 20 to 30% can save 1 to 2% on fuel costs. That might not sound like much. But for an airline operating thousands of flights per day, 1% of fuel costs is tens of millions of dollars per year. During the 2008 financial crisis, when oil prices spiked to $140 per barrel, airlines were desperate to cut costs. Everything was on the table, removing in-flight magazines to save weight, reducing water in lavatories, cutting back on cleaning. Cabin air? Also on the list. There's no public record of airlines explicitly saying, "We're reducing airflow to save money." But there were complaints. Flight attendants reported stuffier cabins. Passengers complained of headaches and fatigue more frequently. And the FAA didn't step in because technically, airlines were still meeting the minimum ventilation requirement. After COVID, when airlines wanted to reassure passengers, they claimed they were running ventilation at maximum rates. But again, no verification. Just trust us. Why, HEPA isn't everywhere. If HEPA filters are so effective, why don't all planes have them? Cost. A HEPA filter for an aircraft costs a few $100s, not a huge expense. But it's not just the filter, it's the housing, the ducting, the increased airflow resistance, which requires more powerful fans, which means more weight and fuel consumption. For a brand new plane, adding HEPA filtration is easy. For an older plane, retrofit costs can run into the hundreds of thousands of dollars per aircraft. And if you're an airline running a fleet of 300 planes, many of which will be retired in 5 to 10 years anyway, spending millions on retrofits doesn't make financial sense. So older planes, especially regional jets and budget carriers, often don't have HEPA. COVID changed the calculus a bit. Some airlines fast-tracked retrofits because passengers demanded it, but not all. As of 2024, most major airlines claim their mainline fleets are HEPA-equipped. But regional jets, budget carriers, it's hit or miss. The regulatory gap. Here's the frustrating part. There's no federal requirement in the U.S. that commercial aircraft use HEPA filters. The FAA regulates safety, structural integrity, engine performance, fire suppression. But cabin air quality? Not really. The minimum ventilation standard, 10 cubic feet per minute per person, was set in the 1960s. It hasn't been updated. There's no requirement for HEPA filters, no requirement for real-time air quality monitoring, no requirement that airlines disclose their ventilation settings. Why? Because the FAA's job is to prevent planes from crashing, not to regulate comfort or health. And as long as passengers aren't passing out from lack of oxygen, the system is considered safe. Other countries are stricter. The European Union Aviation Safety Agency, EASA, has pushed for higher standards. Some Asian carriers voluntarily exceed FAA minimums. But in the U.S., it's largely up to airlines, and airlines predictably do the minimum required unless there's a competitive reason to do more. The bleed air debate. Remember aerotoxic syndrome? The concern about contaminated bleed air? This issue hasn't gone away. Flight attendant unions, particularly in Europe, have been pushing for years for airlines to phase out bleed air systems entirely and move to electric compressors like the 787. The response from Boeing and Airbus? It's not necessary. Bleed air is safe. Fume events are rare. The benefits of electric systems don't outweigh the costs. But here's the thing. If bleed air is so safe, why did Boeing design the 787 without it? The official answer is that the 787's electric architecture allowed for other improvements. Better cabin pressure, equivalent to 6,000 feet instead of 8,000, higher humidity, more efficient systems overall. The unofficial answer? Boeing knew bleed air was a liability. If they could design a plane without it, they would. And they did. But retrofitting the entire global fleet? Not happening. So we're stuck with a patchwork. Some planes with bleed air, some without. Some with HEPA, some without. Some airlines running ventilation at max, others at minimum. And passengers? They have no way to know which plane they're on. The reality check. So after all of this, the engineering, the history, the economics, what's the actual answer? Is the air on planes safe? The honest answer, mostly yes. But with caveats. If you're on a modern aircraft, 737 MAX, 787, A320neo, A350, with HEPA filtration and the airline is running ventilation at normal rates, the air you're breathing is probably cleaner than most indoor spaces. The combination of fresh outside air, HEPA filtration, and rapid air exchange every 2 to 3 minutes makes it hard for airborne pathogens to linger. Studies have shown that your biggest risk on a plane isn't the air, it's the surfaces. Tray tables, armrests, lavatory door handles, and the person sitting directly next to you, because close proximity trumps air filtration. But if you're on an older plane without HEPA, or if the airline has reduced ventilation to save fuel, or if there's a fume event and you're inhaling engine oil vapors, the risk is higher, and you have no way to know. The things airlines won't tell you. Airlines love to advertise their HEPA filters and air exchange rates. What they don't advertise: 1. Not all planes in their fleet have HEPA. Check the specific aircraft type, not just the airline's general claims. 2. Ventilation rates can be adjusted. There's no guarantee the system is running at maximum. 3. Bleed air contamination is rare, but not zero. Fume events happen. If you smell something chemical or oily, report it immediately. 4. Regional jets often have lower standards. Smaller planes, older fleets, less filtration. 5. There's no real-time monitoring. Air quality isn't displayed anywhere. You're trusting the airline. What you can do, If you're concerned about cabin air quality, here's what actually helps. 1. Choose newer aircraft when possible. Boeing 787, Airbus A350, A320neo family. These have better systems. 2. Wear a mask. Even on planes with HEPA, masks reduce your exposure to respiratory droplets from nearby passengers. N95 or KN95 if you're serious. 3. Adjust your overhead air vent. Point it at your face. This creates a small air curtain that pushes away particles from people around you. 4. Wipe down surfaces, tray tables, armrests, seatbelt buckles. The air might be clean, but surfaces aren't. 5. Stay hydrated. Cabin air is dry, usually 10 to 20% humidity. Dry mucous membranes make you more susceptible to infection. 6. If you smell something chemical, report it. Fume events are taken seriously. Don't ignore it. The bigger picture. Here's what frustrates me about this whole issue. The technology exists to make cabin air as safe as possible. HEPA filters work. Electric air systems eliminate bleed air contamination. Real-time air quality monitoring is feasible, but it's not required. And airlines operating on razor-thin margins aren't going to do more than they have to unless passengers demand it or regulators force them. COVID-19 was supposed to be a wake-up call. For a while it was. Airlines invested in upgrades, touted their air quality, ran studies. But now, masks are gone. Ventilation rates are back to pre-pandemic norms. The urgency has faded. Until the next pandemic, or the next major fume event, or the next lawsuit from flight attendants with neurological symptoms. And then we'll have the same conversation all over again. The unasked question. Here's the question nobody wants to answer. If cabin air is so clean, why do so many people get sick after flying? You know the experience. You take a flight, you feel fine during it, and 3 days later, you're down with a cold or the flu. Is it the air, the surfaces, the stress of travel suppressing your immune system, close contact with infected passengers, all of the above? Probably all of the above. But airlines would rather talk about HEPA filters than admit that flying is inherently a high-exposure environment. You're in a confined space with 150 to 300 strangers for hours. Some of them are sick. You're touching the same surfaces they touched. You're breathing air that, even with HEPA filtration, spent time in their lungs first. The air system does its best, but it's not magic. So that's the air up there. It's a system designed by engineers who understand fluid dynamics and thermodynamics. It's regulated by agencies that care about safety, but not necessarily health. It's operated by airlines that care about costs. And it's invisible to passengers who have no choice but to trust that it's working. Most of the time, it works well enough. Modern aircraft with HEPA filters and proper ventilation are impressive feats of engineering. The air you breathe at 35,000 feet is, in many ways, cleaner than the air in the terminal you just left. But the gaps, the older planes without HEPA, the airlines cutting airflow to save fuel, the lack of transparency, those gaps matter. Because when you're sitting in 23C, listening to the guy in 23B cough for 2 hours, you deserve to know. Is this air actually protecting me? Or am I just hoping for the best? The next time you board a plane, look up at those little vents in the ceiling. Air is flowing. It's being filtered. It's being exchanged every few minutes. But it's also being controlled by systems you can't see, adjusted by people you'll never meet, and regulated by standards that haven't changed in 60 years. The air up there is better than you think, but it's also more complicated than airlines want you to know. This has been hours deep. Thanks for flying with me tonight. If you want to go deeper on any of this, the engineering specifics, the aerotoxic syndrome debate, what happened during COVID, let me know in the comments. We've got more investigations coming, safe travels, and seriously, wipe down that tray table.